Hello everybody from the special session Recent Progress in Nonlinear PDEs and their Applications. My name is Aelson, and today I'm going to talk about improved regularity for a class of non-local elliptic equations with an asymptotic property. This is a joint work with my former master's advisor, Aelson dos Prazeres. And before start, I would like to thank especially the organizers of this special session for this opportunity, and I also would like to thank everybody that is going to spend some time to watch this poster presentation. Okay? So, the main problem here is to establish C1 sigma minus 1 regularity estimates for viscosity solutions of this equation right here, okay? And when I say C1 sigma minus 1 minus, I mean C1 alpha for every alpha such that 1 plus alpha is strictly less than sigma. Okay. The main operator here is a non-local operator, which is elliptic to the class L0 and is under an asymptotic regime. And this is related to the notion of the non-local version of the recession operator, okay, that I'm going to discuss later. The background for the regularity theory concerning non-local elliptic equations starts with a paper from Caffarelli and Silvestri, and they essentially deal with solutions of an homogeneous equation, which is uniform elliptic, where this notion of uniform elliptic is adapted to the non-local case. Okay. In fact, in this paper, they make precise what is this notion of uniform ellipticity. And to do this, they define the extreme operators, which are essentially the same as in the local cases. They are the supremum and the infimum over a class of linear operators. Linear operator in this case is this operator here, which is an integral with a function k, which satisfies some assumptions. For example, the class L0 is the class of kernels that are comparable to the ones of the fractional Laplacian. And it is in this class that there are available results like an ABP estimate, Harnack inequality, and Hilde regularity results for the solutions. And to obtain C1 alpha, Caffarelli and Silvestri in this paper here need to consider a little bit more of regularity on the kernels, okay? The next paper is also a paper by Caffarelli and Silvestri, a paper by approximation, in which essentially they extend the previous results for equations like this. Equations with coefficients and a bounded right-hand side. And to do this, they need to develop an approximation method. Okay. And what they do is to consider the main operator here, for example, L0, which is close in some appropriate sense to an operator to the class L1. The class L1 is a subclass of the class L0 of kernels whose derivative are the behavior of the derivative of the kernels are comparable to the derivative of the ones of the fractional Laplacian. Okay. And there are a lot of papers. For example, there are the third paper by Caffarelli and Silvestri, in which they deal with a version of the Evans-Krilov theorem for concave equations, and they deal with solutions to this homogeneous equation right here, where the linear operators here lies in the class L2. The class L2 is a subclass of the class L1, where the action of the kernels behaves like the action of the kernel of the fractional Laplacian. Okay. And in this paper, they prove 6 sigma plus alpha estimates. Another very interesting paper is this paper from Serra, in which he proves also six sigma plus alpha estimates for concave equations, but for equations that are elliptic to the class only L0, not L2. And to do this, they need to pay a price, and the price he pays is that he needs to consider a little bit more regularity on the data. There is also this very interesting paper from Denis Krivitsov, in which he proves U1 alpha for non-local elliptic equations to the class L0, in which he develops a perturbative argument. Okay. The key novelty in our paper is to bring C1 sigma minus 1 minus estimates, that is improved regularity, and to bring this strategy of the recession operator to the non-local case. Okay, we will see more precisely what are the main assumptions. Okay, and there are a lot more of papers that deal with regularity. These I brought here are only a few. Okay, so the basic setup. Since we are dealing with elliptic equations, the natural notion of solution is the Crandall-Lyon's viscous solution type, which says that, for example, for a subsolution to this equation right here, if we have the function u and a C2 function phi that touches from above the solution u in a neighborhood n, then we have this inequality here holding the classical sense for a function psi of this form. And it's clear from ellipticity and Taylor's approximation theorem that we can change this function, this C2 function here, for polynomials of second order, and the neighborhood can be taken as a ball centered at the touching point. Okay? An important notion here is the notion of convergence. We say that a sequence of non-local operators is weakly convergent to a non-local operator I in a set omega if for every point in every test function v of this form we have local uniform convergence. Okay, and this notion of convergence is very important, for example, to develop stability results and compactness results. To exemplify, if we have a sequence of non-local operators in the class L0, this sequence is always weakly convergent up to subsequence to a non-local operator I in the same class. Okay, and this notion, this compactness result, is very important to define the non-local recession operator that we bring in our paper. It is the main definition of our paper. And let's say we have a L0 sigma elliptic operator, we denote by I star the recession operator associated to I as a subsequential limit of this family here, where this family is this family right here, this scaled family. And it's not very hard to see that from the ellipticity condition that this family lies in the same class of ellipticity of the original operator, and therefore the subsequential limit by the compactness results of Caffarelli-Silvestri also lies in the same class of ellipticity. Okay, and essentially what this recession operator is doing is to catch the behavior of the non-local operator at the infinity. Okay, we will see how this works a few slides ahead. Okay, but first let me give some remarks on this definition of recession operator. For example, under the uniqueness of the recession operator, we have homogeneity of degree 1. Okay, We also have a remark of the rate of convergence of the family by mu. More precisely, what I want to say is that if, for example, the recession operator is homogeneous of degree 1, we have this rate of convergence here, provided the test functions here meet this assumption here, okay? And this is nothing new. In fact, this is just an analysis on what is the dependence of the models of continuity of this family here, okay? And this results as a local counterpart that can be seen in these three papers here, a paper from Silvestre and Teixeira, a paper from Pimentel and Teixeira, and a paper from Pimentel and Sons. These are very interesting paper, which treats the local version of the recession operator. There are more, but I brought here these papers because it was very inspiring to us, okay? So let me talk about the main assumptions of our paper. First of all, we consider a L0 elliptic operator, which is translation invariant, that is, no coefficients. This is just for simplicity because the same program could be done for the non-translation invariant case, okay? The second assumption is that the recession operator has C sigma estimates, and the third assumption, and more important, is this scaling type assumption, which I'm going to discuss after I give the examples. For the first example, let this family be a family of linear operators in the class L2, and consider this non-local operator here. This is a non-local operator to the class L0, where this operator here is this one. Is a multiple of the linear operator plus the sine function. This is a L0 elliptic operator such that the recession operator will be an infimum of linear operators. And from the Evans-Klisov theory, from Caffarel and Silvestre, this operator has C sigma plus alpha estimates. The second example is something like this. Let G1, GK be real functions satisfying these assumptions here, okay? And let I be this non-local operator. I'm sorry for this mistake here. I have V here, okay? This is a non-local operator to the class L0 such that the recession is the fractional Laplacian, okay? A typical function gi, just to exemplify, works like this. This is the behavior of a typical function gi, okay? The third example is it's a non-local disguise. It's a local disguise, in fact, for a non-local operator. More precisely, what I want to say is that let u from Rn to R be a function, and define this quantity here, okay? And let d sigma u of x be this symmetric matrix here. Now take a lambda-lambda elliptic operator, local operator, such that it satisfies this assumption here, okay? Now we consider this operator, which is an operator elliptic to the class L0, and such that the recession operator will be the fractional Laplacian, okay? For those who are interested in this class of equations, I recommend the paper from Huyu, the small perturbation paper from Huyu, okay? So now let's get back to the assumption A3, the scaling type assumptions. What is this saying? Essentially, you can ignore here this factor mu here, and look only for the lambda factor, okay? What is it saying? This is saying that I need to the non essentially this is saying that I need that the nonlinearity stays outside of the integral and not inside the integral. And the main reason for this is that since scaling for non-local equations comes from an integration by parts, if we put the nonlinearity inside the integral, this factor here will cancel out, and this is very bad for iterative purpose. For example, if you consider this equation here, where I put the nonlinearity inside the integral. For example, if you take v as this function here, u lambda to the power of 1 plus alpha, then v solves a very good equation. I lambda v is equal to lambda sigma minus 1 minus alpha f. But this operator here is not very good because it has a factor lambda 1 plus alpha. When I apply this operator to general functions, let's say w, it is like this. And since I don't have the factor of lambda sigma here, I can't control this factor here, and therefore the convergence to the recession operator, it is going to be delayed every time we do scalings. So it is very bad for iterative issues, for iterative techniques, okay? And therefore we need to avoid this kind of operator. Okay, so to obtain the main theorem here, we need to establish an approximating scheme which is based on this flatness lemma. Essentially, if I have a solution of this equation here, where the function v has a modulus of continuity in a ball of radius r greater than 1, a big R, and has this growth at infinity, then the function v is close to an I star harmonic function, okay? And the idea to this flatness lemma is to use compactness. We assume it is false to find sequences mu j, vj, fj, eta j, and this growth condition here and this models of continuity assure that the sequence vj converges almost everywhere to a function and in the weighted space, and now we pass to the limit to get the desired conclusion, okay? And finally we can pass to the improved regularity result, which says that if I have a viscous solution of this equation where the operator satisfies the assumptions I stated before, then we have C1 alpha for every alpha less than sigma minus 1 plus an uniform estimate. And the idea for the proof is to use scalings, and then it's all a matter of approximate u in a C1 alpha profile by a sequence of linear functions. And this is done by analyzing what type of equation this function's wk here satisfies. They will satisfy a very good equation, this equation here, where the operator here is, when applied to general functions, will be lambda sigma k, lambda minus k, 1 plus alpha, the factor mu minus 1, lambda k, 1 plus alpha, v, lambda minus k, lambda kx. And from the assumption A3, we can write this operator here as lambda k sigma minus 1 minus alpha mu v of x. And that's why we need assumption A3, so that the scaling does not delay the convergent. And these are only the first steps. There are a lot of calculations that I'm not gonna put here, and my presentation finishes here, okay? Thank you very much.